Thanks, Miles, for the introduction, and thank you all for coming to the talk. I'll talk about how we at SailThrough built a recommendation system using multiple different diverse features and what role Spark played in the development. And this is joint work with my current and former colleagues. Max and David are at SailThrough right now, and my former colleagues, Alex and Jeremy. So let me first tell you why we wanted to build a recommendation system at SailThrough in the first place. So what is SailThrough? So SailThrough is essentially a customer retention cloud where marketers at media and e-commerce companies, they use our tool to reach out to their customers, to their users. And the end result of marketers using our technology is that it results in maximizing the lifetime value of users. And the marketers do this using multiple different channels, including email, social, website, mobile, and even offline communications. And all these communications are powered through the SailThrough platform, and eventually it leads to increased revenue, one-to-one personalized experiences, and naturally engagement. And we wanted to do this recommendation system project to further enhance the one-to-one experiences that users have with their clients. And I've just listed 5 of the different clients that we have from media and e-commerce space. But right now, the SailThrough platform is being used by over 400 different clients. So let me tell you about the recommendation system problem that we had. So the problem is fairly standard in terms of recommendation systems. For a given client, we have the space of all their users, and we have the space of all the catalog of items that that client has. And what we wanted to do was, for every pair of user and items, we wanted to figure out whether that user will buy that particular item in the future or not. And the predictive part of this application is important because in the recommendation system that we wanted to build, we wanted the marketers to know how to use that information. By telling the marketers that this particular item has a certain chance of being purchased or not purchased, the marketers would know how to act on that information. So now that we have framed the problem in this way, there are many different methods that we can use to actually solve this problem. One of which is provided in the Spark MLlib library, which is essentially matrix factorization. And there's a very simple API to actually use it in practice. And you can get started with it very easily. And there are a host of different other algorithms that one could use based on item-to-item similarity, content-based recommendation systems, and various nearest neighbor-based methods. And I'll note that the current recommendation system that we use at SailThrough is actually a content-based recommendation system. And our main goal was to come up with something that's much more powerful than that. And just to point out the advantages of these methods, if you take each of these methods, there's probably some kind of open source scalable implementation of it available that you can easily use and get started with to build like a first pass recommendation system. But what we found out very soon was that it was not very easy for us to incorporate additional features into these algorithms. You could somewhat do that with the implicit feedback version of matrix factorization algorithms, but in our experience, the performance of it wasn't as good as what we wanted it to be. And what we really wanted to build was a system where we could treat additional features explicitly. Now, what do I mean by additional features? What features am I talking about in our context? And these are basically a bunch of user and item level features. So on the user side, you can think of the location being recorded, the browser being recorded, and various user activity aggregated in a particular interval, like the number of URL views, the number of emails that are sent to that user, the number of emails the person clicked, and so on. So that's a whole set of user-level data that we record. On the other hand, we record a lot of item-level data. So these are natural things such as the image of the item, the description, the title, the price, and various other metrics about the item themselves. And the next set of data or features that we have are essentially the user item interactions. So for example, whether a particular user purchased a particular item or not, whether a particular user viewed a particular item or not. And there are multiple different kinds of data points that we have, such as cart abandonment and so on, about various user and item level interactions. So what we really wanted to do was come up with a framework in which we could easily integrate these user-level features, these item-level features, and these user and item interactions in a very easy way to actually generate meaningful recommendations. So in the next few slides, I'll go over the framework that we outlined, which is fairly simple, and then go into some of the implementation details. So whenever you're doing any kind of predictive modeling, you want to divide your time into two intervals. One is the prediction interval, and from that prediction interval, you're going to gather features, and you want to look at those features and see how those features influence behavior in some response interval. And the response interval over here corresponds to whether a purchase was made or not. So the next question is, how do we actually aggregate the features over here? And it's fairly simple. So all we do is we take, for each row, which corresponds to a user item pair, we take the user level features that I described previously. We take the item level features, of course encoded in a certain manner. And then we look at the user item interactions, whether that particular user bought that particular item or not. And then we add that in as more columns in our matrix. And then finally, the response is whether a purchase was made or not. And then we add another column, which are basically user item features that are derived from these user item interactions. So for example, you could take the matrix factorization algorithm, apply it to the URL page view history data. You'll get user level features, you'll get item level features, which are essentially vectors of numbers. You can add that in that user item features column, and you can also add in the product of those two numbers as another feature. So in this way, we are using multiple different collaborative filtering algorithms to derive additional features from the data that we already have in the system. So what I've talked about so far is a framework in which we could easily integrate multiple different features, where the end result of that is we transform a recommendation problem into essentially a binary classification problem. And once we have done that transformation, there are a lot of different tools and techniques out there for solving binary classification, and then we make use of them to actually build the final recommendation system. So what I'll talk about next is the actual implementation and how we use Spark in this project. So everything obviously starts with the data that we have. The data that we have stored in S3 are essentially structured tables about all the different kinds of features that I outlined before. So these are URL viewed purchases, various user level data, item level data, and so on. And we aggregate all of this data using a separate Spark job, which grabs data from our database and then structures them into nice tables so that all the downstream processing can be as easy as possible. So from these tables, we basically launch two sets of Spark jobs. So the first set of Spark jobs are basically doing an item-to-item similarity computation. And I'll talk towards the end about why exactly we are doing that over here. But essentially, we're finding similarity between items. And the second set of Spark jobs are essentially a bunch of filtering operations that we are doing on each table that we have saved in S3. And I'll talk a little bit about why we're doing that. But the end result of this is we're able to scan through an extremely large data set. And the end result is we store the result in S3, which is pretty small. And we can actually do all our further computations in R and using XGBoost to build models. So this is not using Spark R. This is actually standard R. And it's able to load all the data after the filtering step into memory and then doing all the feature building that I talked about before. And then we do, for modeling, we use GBMs using XGBoost, and that's where we are doing all our model building, validation, and a lot of the reporting as well. And the end result is we take the models that we built using XGBoost, and we also take the item-to-item similarity matrix that we built, and then we combine them together to get the final recommendations. So that's an overview, a very high-level overview of how we built this system. What I'll talk about next is some of the things that we learned when implementing some of the first two steps in Spark. So the first thing that we learned was we really need to know the partitioning of our data. And so for example, when we started playing around with Spark the first time, we came around Spark SQL, and one of the computations that we needed to do was we had a URL view data, and we needed to select the number of users, or we needed to select the users that had visited a certain number of URLs. So this is a simple group by, or select, group by, and a filter statement using Spark SQL. And what we quickly realized that this was very inefficient, especially for some of our bigger clients. And the inefficiency was obviously due to the fact that we were not utilizing the partitioning of our data. And the way our data is partitioned, so all the data for a particular user actually belonged in one partition. So for example, if I were in this data set, all my data would belong into one particular partition. So then what we quickly realized is that map partitions is actually our best friend in this case. So for all our filtering operations, we ended up using map partitions very heavily. And the way this works is you essentially do a map operation on the partition itself, and then you end up writing a Python function which basically is doing a Python computation, counting the URLs in that partition, and then returning the users by doing the filtering. So this turned out to be very efficient, at least compared to the older, the first version of what we started out with. And it also gave us a good understanding of when to use map partitions, and also think very carefully about the partitioning of our data before doing any further computations. The next thing that we learned, and this was talked about in some of the earlier talks as well, is we should really think carefully about breaking up our applications into small chunks when doing computations, especially long-running Spark jobs. So as an example, one of the things that we wanted was we wanted to get the users that had visited a certain number of URLs in the past, and then what we wanted to do was filter another data set on those users. So we could easily do this using these two computations like this in one Spark session. But what we realized is, again, this was leading to some RAM issues, and it was turning out to be inefficient. So what we ended up doing was we basically split this into two jobs. So in the first job, we do the user computation, collect it, and then save the result to S3. And then in a separate job, we basically read the results back from S3 and then do the filtering operation again. So it's a very simple thing to do, but we essentially break up our applications this way. And the result of all of this was we have multiple, I would say about 100 different filtering operations going on. And we ended up breaking all of them into small chunks and connecting them together using a scheduler. So, and basically specifying the dependency amongst these different Spark applications. So for example, we'll have an operation A that would run, and after it would get completed, it would save the result to S3, and then a job B would run, and it would read the result from S3 for A, and after B would complete, a bunch of other Spark applications would basically run. And we manage all of this dependency and the scheduling using a tool that we have open sourced at Sailthrough called Stolos. And we have multiple such jobs running for multiple different clients. And to manage all the tasks, multiple tasks that we are running, we use Mesos as a cluster manager. And we package all our applications, be it Spark, Python applications, or R applications, all of it using Docker, and that really easily gets us to actually deploying code into production. So the end result of all of this is we actually get a model, and then we can basically do a computation that says, for every user, what is the probability that a user will buy a particular item? So that's the end result. However, what we quickly realized was, well, we can do these computations for, say, 500 items for every user. We can do these computations for, say, 1,000 items for every user. But it's really questionable if we really need to do these computations for, say, 5,000 items for every user. And if you can imagine, there are like millions of users and over 5,000 items, just saving the results of that alone is a pretty difficult task. So what we had to do was think about ways in which we can somehow avoid computing or applying the model to, say, more than 1,000 items, and somehow do some kind of reduction so that we can basically make this much more scalable. And that's where doing the item-to-item similarity actually helped. So the way we do this, we just use the compute similarity functions that's available in Spark MLlib, and we point it to the URL visitation data. And it was actually very easy to do. And the end result of this is, for every item, we get a list of similar items and scores associated with them. And I won't go too much into the details since I don't have that much time, but essentially we take the result of the item-to-item similarity computation and then look at for every user, we look at what they have done in the past and somehow filter the 10,000 items that we have down to a much smaller set, and end up applying our model that we have trained in the past to those items for every user. And that's how effectively we are scoring all the items in the catalog, but really what we're doing is using the item-to-item similarity computation to reduce the amount of things that we need to score. And now this is not actually how we do the recommendations. For the actual recommendations, what we're doing is we're actually doing another computation after this, which is another Spark job, because what ends up happening here is that the probabilities that we end up computing are basically popular items get a higher probability just because they have much more data. So to solve for that, what we do is an affinity calculation, where for each user and item, instead of outputting the probability, we output the affinity that user has towards the item when compared to an average user. And that really, one of the byproducts of that was this very nice plot, where essentially this plot, so the red dots correspond to to items that are highly ranked, and the yellow or greenish are low-ranked items. So it led to a nice clustering of, so this is essentially a bi-clustering of the items and the users. So if a marketer looks at this, he or she would say, okay, this group of items are basically have a high affinity for a particular group of users as well. So it would make sense to offer these items to these users, and so on. And there are multiple different ways in which marketers can use this information about the grouping and the similarity between the items that we have computed and design various innovative strategies for marketing. And we're very, very excited to actually test this out in production. So to summarize, what I've talked about is how we were able to integrate multiple diverse features to build a recommendation system. And in order to utilize Spark, we had to be very careful in designing small Spark applications, and we were able to connect them all together using a dependency graph, and we were running them in Mesos and using Docker. And in future, what we really want to do is do more Spark development for sure, convert some of our R jobs that we have slowly into Spark jobs, and that may speed up our computations and make our jobs much more efficient as well. And we also want to look into using Mesos as a cluster manager, because right now we're actually running Spark in local mode because we're reading all the data from S3, and we really want to be able to utilize this feature going forward. With that, thank you for all for listening, and I'll be happy to take any more questions.
Back here. Thanks for the talk. For the scheduler and the tool which you open sourced, why don't you use the Apache Uzi? Isn't both of them do the same thing? Because Uzi do the scheduling and the dependencies between the jobs, and you can plug into it Spark jobs or whatever you want.
Okay. I'm not really sure about why we built something in-house. I think at the time when we were doing this, there was no good alternative that we found. This was about 1.5 years ago. And we use this in our other applications as well, so it felt very natural to use this in this application. But it's definitely something that we can look into to further improve the infrastructure. Thanks.
Thanks for the presentation. So you mentioned using collaborative filtering models, multiple collaborative filtering models to produce derivative features that you could then use in binary classification. Could you speak a little bit more in detail about that or provide an example?
Sure. So I think right now what we're using are multiple nearest neighbors based approaches, where we essentially look at essentially they're nearest neighbor based models. So we're essentially predicting in that prediction interval what is the probability that particular user item pair is going to be bought. And that essentially goes in as a feature into the models and you also have the response that you're looking into. I can talk offline in detail about the algorithm. It's difficult to summarize those in like a minute or two.
Thanks.
But I'd be happy to talk offline about them.
So are the models trained and basically, is this for offline, right? Do you have a online like a deploying process for this to run the models in real time?
Yeah, so all the models that we're training are in batch mode. And then what we do is we make predictions and then we send out those predictions onto the user profiles. And then they get used by the marketers. So there is a delay, so it's not happening real time, there is a delay. But in the future, we definitely want to look into how we can use these recommendations and the predictions in a real time manner.
Any other questions?
Hi, you mentioned that you're using Mesos as a cluster manager. Did you try it with any other cluster manager, or is that? I just want to know if there's a comparison, and if there was a comparison, if you found something.
I think the reason we're using Mesos is because we were using it in our other projects, and our whole infrastructure is built on top of that, using Mesos and AWS Spot instances and everything. We haven't tried anything else yet, because we have invested heavily in using that, but it's definitely something we are constantly looking to improve.
If that's it, let's give Div another warm round of applause.